December 16th, 1944, 5:30 in the morning, the Ardennes Forest, Belgium. Feldwebel Klaus Richter of the 12th SS Panzer Division has been in the Wehrmacht for 4 years. He has fought in France. He has fought on the Eastern Front. He has seen artillery bombardments that turned forests into open fields and open fields into craters. He knows what incoming fire sounds like and what it feels like, and what it does to the men around him when it arrives. He is, by any measure, a veteran who has made his peace with the specific physics of how artillery kills. He has never heard anything like this. The shells are not landing. They are detonating 30 feet above his men's heads. Not one shell, not a ranging error, not a proximity accident. Systematically, methodically, every shell in the barrage is exploding in the air above the exact altitude where a man standing in a trench is still fully exposed. Too high to be stopped by earthworks, too low to scatter before the fragments arrive. The men in the foxholes that would have protected them from direct hits are dying in those foxholes from fragments arriving from above and behind, from angles that no field fortification in the history of ground warfare has been designed to stop. In 3 minutes, Richter watches an entire battalion of German infantry attempting to cross open ground simply cease to exist as a military unit. The survivors who find him have the specific expression of men who have encountered something for which their entire vocabulary of combat is inadequate. They keep repeating the same phrase, Die Luft tötet, the air kills. Richter writes in his field diary at 0630 hours, the Americans possess a new weapon that defies all tactical doctrine. Our men are being slaughtered in their foxholes by artillery that explodes in the air above them. There is no defense. There is no cover. Death comes from the sky itself. He is correct. And he is also missing the most important fact about what just happened to his battalion. The shells that killed them did not explode because a gunner calculated the correct fuse setting. They exploded because each shell knew, by itself, how far it was from the ground. The shell thought. This is the forensic account of how that became possible. It begins not in an American laboratory, but in a British one, in October 1939, when a scientist working at an air defense facility in Christchurch, England, stared at the mathematics of anti-aircraft fire and concluded that the numbers were so bad they constituted a national emergency. It runs through one of the most significant scientific intelligence transfers in history, delivered in a black metal box aboard a ship in Halifax Harbor in September 1940. It runs through a physicist in a building in Washington, D.C., who had been crying over London on his radio and was handed 4 weeks later the specific problem he needed to solve. It runs through the most secret classification decision of the entire Allied war effort, a decision so sensitive that the weapon was used for 2 years in the Pacific before anyone was allowed to fire it over European soil, for fear that one unexploded shell in German hands would undo everything. It ends on December 16, 1944, in the Ardennes, where the shell the British imagined and the Americans built arrived in the exact battle where the Germans most needed an advantage they no longer had. October 30, 1939, Christchurch, England, the Air Defense Experimental Establishment. The number was 8,500. That was how many anti-aircraft shells British gunners had fired, on average, during the First World War to destroy one enemy aircraft. 8,500 rounds, per aircraft. The mathematics of anti-aircraft gunnery in 1918 had been this bad for a specific technical reason. A shell fired at an aircraft had to detonate at the precise moment it passed within lethal fragment range of the target. The lethal fragment radius of a standard 3.7-inch anti-aircraft shell was approximately 15 feet. The aircraft it was being fired at was moving at between 80 and 120 miles per hour in 1918. The window of time in which the shell was in lethal range of the target, assuming the shell's trajectory intersected the aircraft's flight path at all, which it usually didn't, was measured in fractions of a second. Achieving detonation within that window required a time fuse, a mechanical clockwork mechanism set before firing to expire after a calculated interval corresponding to the altitude at which the gun crew predicted the shell would intersect the aircraft's flight path. The prediction required estimating the aircraft's altitude, airspeed, heading, and rate of climb or descent simultaneously, computing the fire control solution, setting the fuse, loading the shell, and firing, a process that took between 5 and 15 seconds under ideal conditions, by which point the aircraft had moved and the calculation was already wrong. The gunners were not bad at their jobs. The job was, by the mathematics of time-fused gunnery against fast-moving targets, essentially impossible to do well. 8,500 shells per kill was not a performance failure. It was the theoretical optimum for the technology available. By 1939, the number had gotten worse. Aircraft were faster, flying at higher altitudes, less predictable in their flight paths. The Heinkel HE-111 bomber that would form the backbone of the German bombing campaign against Britain flew at 220 miles per hour at altitudes above 15,000 feet. At that speed and altitude, the fire control problem for a time-fused anti-aircraft shell had become, in the assessment of the British anti-aircraft establishment's own analysis, effectively insoluble with existing technology. The standard estimate for the coming war was that German bombers would require somewhere between 10,000 and 20,000 shells per aircraft destroyed, worse than the First World War, in a war where the bombers would be larger, faster, and coming in formations of hundreds. Britain, which was going to need to defend its cities and factories and harbors against a German air campaign that its own intelligence services were projecting would involve hundreds of bombers per raid, did not have enough ammunition to sustain a defense at those kill ratios. The mathematics were existential. If the numbers couldn't be improved dramatically, Britain would run out of shells before it ran out of German aircraft. The Battle of Britain would be lost not by the pilots of Fighter Command, but by the arithmetic of anti-aircraft gunnery. A scientist named William Boutmont, working at the Air Defense Experimental Establishment in Christchurch, submitted a proposal in October 1939 that his colleagues initially treated as science fiction. He proposed a fuse that would not rely on a pre-calculated timer at all, a fuse that would, instead, continuously emit radio waves from the nose of the shell itself, waves that would bounce off any nearby target and return to a receiver in the same shell, triggering detonation automatically when the reflected signal exceeded a threshold that meant the shell was close enough to be lethal. No calculation, no prediction. The shell would sense its own proximity to the target and decide by itself when to explode. The concept was sound. The engineering was impossible. A radio fuse small enough to fit inside an artillery shell would have to contain a complete miniature radar system, transmitter, receiver, amplifier, detonation circuit. You would have to generate power from its own internal battery. You would have to operate across temperature ranges from -50 to +100 degrees Fahrenheit. And it would have to survive being fired from a gun barrel, which meant surviving acceleration forces of approximately 20,000 times the force of gravity, while spinning at 30,000 revolutions per minute, inside a steel casing that was simultaneously being forced through a rifled barrel by a propellant charge generating pressures of 50,000 pounds per square inch. The vacuum tubes that were, in 1939, the only available active electronic components, the tubes that made radios and amplifiers and detection circuits function, were made of glass. They were built with hairline wire connections. They operated on the principle that electrons traveling through a vacuum between electrodes could be controlled by voltages applied to intermediate grids. This principle required that the glass envelope maintain its shape, that the electrodes maintain their spacing, that the wire connections maintain their integrity. Under 20,000 times the force of gravity, spinning at 30,000 revolutions per minute, all of these requirements failed simultaneously. Boutmont and his colleagues at Christchurch built working prototypes by June 1940, tested against balloon targets from unrotated projectiles, essentially rockets, which did not spin and did not experience gun-firing acceleration. The tests proved the concept. They also confirmed that no existing vacuum tube could survive being fired from a gun. The engineering gap between proof of concept and fielded weapon was, in the summer of 1940, unbridgeable with British industrial resources. Britain was simultaneously building fighter aircraft, training pilots, expanding its radar network, and preparing its civilian population for aerial bombardment. There was no spare industrial capacity for a development program of the scale and duration that the proximity fuse required. The solution would have to come from America, and the channel for it was a black metal box on a ship. September 6, 1940, Halifax, Nova Scotia. The Canadian Pacific liner Duchess of Richmond. Sir Henry Tizard was 60 years old, a chemist who had spent his career at the intersection of science and military policy. He had been the scientific advisor who had pushed Robert Watson Watt's radar development from laboratory concept to operational network in the years before the war. He understood, from that experience, what it looked like when a technology was ready to change a war and what it required to make that change happen at scale. He also understood, in September 1940, that Britain was fighting for its survival with technologies that it did not have the industrial capacity to fully develop. He was carrying, in a black metal deed box that never left his sight during the crossing, the complete technical details of every significant British military scientific development. Radar systems at multiple wavelengths, jet engine designs from Whittle's program, explosive research, acoustic detection technologies, and the proximity fuse circuits that Boutmal's team had developed at Christchurch. The Tizard mission, as the delegation was already being called, was the largest transfer of military scientific intelligence between sovereign states in the history of warfare to that point. Britain was sharing secrets it had spent years and significant resources developing with a country that was not yet at war and had no treaty obligation to use them. The gamble was straightforward. If America developed these technologies at the scale that British industry could not, Britain's survival would be secured. If America stayed neutral and the technologies were captured, the gamble would have failed catastrophically. The delegation arrived in Washington on September 12th. Over the following week, they briefed American counterparts at the Navy Department, the War Department, and the newly established National Defense Research Committee. On September 19th, in a conference room in Washington, the British physicist John Cockcroft, who had been the first man to split the atom in a laboratory 6 years earlier, presented the proximity fuse program to a single American, Dr. Merle A. Tuve of the Department of Terrestrial Magnetism at the Carnegie Institution of Washington. Tuve was 39 years old. He had grown up in Canton, South Dakota, the son of a Lutheran minister, and had discovered his aptitude for physics through a childhood spent building radio sets with his friend Ernest Lawrence, who would later win the Nobel Prize for inventing the cyclotron. Tuve himself had done foundational work in nuclear physics and ionospheric research. He had been appointed 1 month earlier, in August 1940, to lead Section T of the NDRC, the section created specifically to develop proximity fuses. The appointment had not been random. Vannevar Bush, who ran the NDRC and had been looking for someone to lead this particular program, wanted a physicist who understood radio, understood electronics, and could build and lead a team quickly. Tuve fit the requirement exactly. He had additional motivation. In the weeks before the Tizard mission arrived, Tuve had been listening to radio broadcasts about the German bombing campaign against London. He heard the descriptions of children being pulled from rubble. He heard the accounts of neighborhoods eliminated overnight. He turned to his wife Winnie one evening and told her that technology had to find an answer to this, that there had to be a way to stop the bombers. 4 weeks later, John Cockcroft was handing him exactly that problem. Tuve left the September 19th meeting with Cockcroft's circuit diagrams and a mandate from NDRC to do something with them. He assembled his team at the Carnegie Institution's Cyclotron building on Broad Branch Road in Washington, D.C., a building whose original purpose was nuclear physics research and whose new purpose was the most secret weapons development program in the country. The team that gathered there over the following months would prove to be one of the most consequential assemblies of scientific talent in the history of the American war effort, though they operated in conditions of such strict secrecy that many of them could not tell their families what they were working on. Richard B. Roberts, who had worked with Tuve in nuclear physics and understood the behavior of matter under extreme conditions. Lawrence Hafstad, a specialist in nuclear physics. Lloyd Berkner, a pioneer in ionospheric research who had been on Richard Byrd's Antarctic expedition and had learned, in that environment, what it meant to build instruments that had to function under conditions they were not designed for. Henry H. Porter, an expert in acoustics whose understanding of signal behavior in complex environments would shape the fuse's detection circuit design. And a 26-year-old physicist named James Van Allen, whose later discovery of Earth's radiation belts would make him one of the most famous scientists of the space age, but whose wartime contribution would remain classified for decades. Because the problem Tuve gave him was the most fundamental one, the one that everything else depended on. Make a vacuum tube that can be fired from a gun. This was not, on its face, a physics problem. It was an engineering problem of a particular kind. A problem where the failure mode was known and the solution was not. Every vacuum tube Van Allen put in a test fixture and subjected to simulated firing acceleration shattered or failed. The glass envelopes cracked. The electrode spacings shifted. The wire connections broke. The filaments that heated the cathodes, which were drawn from tungsten wire thinner than a human hair, snapped under the shock loads. Van Allen ran hundreds of test sequences, modifying one variable at a time, trying to find the combination of glass thickness, electrode support geometry, filament mounting technique, and wire gauge that would allow the tube to survive what it was being asked to survive. He built a centrifuge to simulate the acceleration forces of gun firing. He built a drop test apparatus to simulate the shock of the propellant charge. He built a spinning rig to simulate the rotational forces of a rifled barrel. Each test destroyed more tubes than it saved. He kept records of every failure, meticulous records, in the belief that a pattern was present in the failures and that the pattern would eventually reveal the solution. This is the method of experimental physics applied to an engineering problem, not intuition, but systematic elimination. The breakthrough came from an unexpected direction. Standard vacuum tube production in 1940 sealed the glass envelope while the tube was being evacuated, a process that left residual mechanical stress in the glass around the seal. Under normal operating conditions, this stress was irrelevant. Under 20,000 times the force of gravity, it was a fracture initiation point, the location where a crack would begin, propagating outward in the fraction of a second between the propellant firing and the shell leaving the barrel. Van Allen's team found that if the sealing process was modified to anneal the glass around the seal, heating it slowly and cooling it under controlled conditions to relieve the residual stress, the tubes survived forces that had previously destroyed them. The annealing process added time and cost to every tube produced. It required modifying the sealing equipment at every manufacturer involved in the program. It required training workers in a process that had no precedent in commercial electronics production, and that produced no visible difference in the finished tube. The annealed tube looked identical to the unannealed one. The difference was entirely internal, entirely structural, entirely invisible until the moment of firing. Convincing production managers to adopt a modification that added cost and time to a component whose improvement could not be visually verified required the specific authority that came from Tuve's office and the specific evidence that came from Van Allen's test records. The first shock-hardened tubes were ready for testing in early 1941. They survived. The basic engineering barrier had been crossed. What followed was not a clean development arc from prototype to production. It was 18 months of iterative failure and incremental success involving more than 40 industrial and academic contractors across facilities from the Carnegie Institution to the Applied Physics Laboratory that Tuve established under Johns Hopkins University in March 1942, a laboratory that began in a garage in Silver Spring, Maryland, and grew into one of the most consequential applied research institutions in American scientific history. The production problem was, in some ways, more difficult than the development problem. A proximity fuse contains 6 vacuum tubes, a miniature battery, a safety arming mechanism, and a detonation circuit, all assembled to tolerances measured in thousandths of an inch, in a steel casing that had to thread into the nose of an artillery shell and survive both storage and firing without any pre-use testing. Every fuse had to work the first time because there was no second time. The quality control requirements were, by any previous standard of electronics manufacturing, unprecedented. Commercial radio manufacturing tolerated defect rates measured in percentage points. The proximity fuse program required defect rates measured in fractions of a percent, because a fuse that failed to detonate was not just a wasted shell, it was an unexploded device that could, if recovered by the wrong hands, compromise the entire program's secrecy. The solution to the production problem came from the same place most American wartime manufacturing solutions came from: the consumer electronics industry. Tuve's team worked with the manufacturers of radio sets, phonographs, and electronic instruments to develop the production techniques for components that could be assembled rapidly by workers without specialized training to tolerances that the component's eventual use required. By the summer of 1942, 87 companies were producing components for the proximity fuse. By 1944, 110 factories and 80,000 workers were involved in the program. Total cost by war's end? Approximately $1 billion in 1940s currency. In August 1942, the first production fuses were ready for live-fire trials against drone aircraft in the Chesapeake Bay. The Navy observers present watched drone after drone fall from the sky on the first or second round fired. They had never seen anything like it. One observer recorded in his report, "It was as if the shells were guided. They were not guided, they were thinking." But before a single proximity fuse could be used in combat, the Allied High Command had to make a decision that reveals more about the strategic intelligence of the war's management than any other single policy choice: where to use them first and where to keep them secret, and why the distinction between these two theaters was the most important operational security decision of the war. The Allies faced a specific and genuine dilemma. A proximity fuse fired over enemy-controlled territory could produce unexploded shells, shells that had malfunctioned or missed their target and landed intact rather than detonating. A German engineer who recovered an unexploded proximity fuse shell could disassemble it, identify its operating principle, and deliver that analysis to German research programs within weeks. At that point, the entire technological advantage disappeared. Germany had the industrial capacity and the electronic engineering expertise to produce its own version, and it would do so. The weapon that had taken 3 years and $1 billion to develop would be replicated in months. The decision was therefore straightforward. The proximity fuse would not be used over European soil until the Allies were confident that German ground forces could not recover unexploded examples in sufficient quantity or time to allow reverse engineering. For 2 years, from January 1943 to December 1944, the proximity fuse was used exclusively in the Pacific and in air defense over Allied territory, where the ocean or Allied-controlled ground ensured that unexploded rounds could not be recovered by the enemy. The first combat use was on January 5, 1943, in the Pacific. The cruiser USS Helena was operating near Guadalcanal when Japanese aircraft came in low over the water on an attack run. Helena's 5-inch guns fired proximity fuse shells. The first Japanese bomber was destroyed by the 5th round. Standard time fuse shells against a low-altitude aircraft required, on average, more than 500 rounds for a kill. 5 rounds. The Pacific results were unambiguous. Against Japanese aircraft, proximity-fused anti-aircraft shells were transformative. The kill ratio improvement was not 10% or 20%. It was not even double. Against low-altitude aircraft, the attack profile that Japanese pilots had refined for ship-killing operations, the proximity fuse reduced the rounds per kill from 500 to 155. The mathematics that had been existential for Britain in 1939 were being rewritten in the Pacific in 1943. The fuse was then deployed against the V-1 flying bomb campaign against London, beginning in the summer of 1944. Possible because the V-1s that were destroyed fell into the sea or into Allied-controlled southern England, where unexploded proximity fuses were recoverable before they could reach German hands. The results against V-1s were the single most dramatic demonstration of the weapon's capability in the entire war. In the first week of V-1 deployment in June 1944, before proximity fuses were available in large numbers, British anti-aircraft guns were destroying fewer than 20% of V-1s that entered their engagement zones. By August 1944, with proximity fuses available in quantity, the destruction rate was 79%. 4 out of every 5 V-1s fired at London was being destroyed before reaching its target. London survived the V-1 campaign because of a fuse the size of a coffee can, built by 80,000 workers whose names appear in no histories, assembled in 110 factories that produced no public records of what they made. The women who assembled them deserve a specific paragraph. The precision required to assemble a proximity fuse, the tolerance work, the soldering of connections measured in fractions of a millimeter, the testing of circuit continuity before the assembly was sealed, was work that required fine motor control, patience, and the sustained concentration that production line electronics manufacturing demands. The American electronics industry, expanding rapidly to meet wartime demand, had discovered what the British and the Germans had not yet institutionalized, that women were better at this work, on average, than men. Not better in theory, better in the measured quality metrics of production, lower defect rates, tighter tolerances, fewer rework operations. The companies assembling proximity fuses hired women specifically for the precision assembly work and found that their production statistics improved. Their names are not recorded in the program histories. The proximity fuse program's institutional memory preserves the physicists, Tuve, Roberts, Van Allen, Berkner, with considerable detail. The women on the production floors are present only in the aggregate statistics of units produced and defect rates achieved. Betty Morrison at the Crosley Corporation in Cincinnati, Marie Collins at the Johns Hopkins Assembly Facility in Silver Spring, thousands of others working on a weapon they were not told the purpose of, building a secret they could not discuss, whose output arrived in the Pacific and the skies above London as a capability their enemies could not explain. December 16, 1944, Elsenborn Ridge, Belgium. 07:15 hours. The proximity fuse had finally arrived in Europe. The operational security rationale that had kept it out of European ground warfare for 2 years had been reviewed and revised in the weeks before the Ardennes offensive. The Allied High Command had concluded that the military necessity of using the weapon in the expected German winter offensive outweighed the continued risk of German recovery of unexploded examples. Germany, by December 1944, was in a strategic position that made a major reverse engineering program for new weapons increasingly implausible in any case. Their industrial base was under sustained bombing, their technical personnel were being consumed by the attrition of the war's final phase, and the time required to develop a counter-technology exceeded the likely remaining duration of the conflict. The decision was made. The shells with the green-painted bands, the field designation that distinguished proximity-fused rounds from conventional ammunition, were distributed to artillery units supporting the American forces facing the Ardennes front. The German offensive began on December 16th. The 2nd and 99th Infantry Divisions, positioned on the northern shoulder of the German attack at Elsenborn Ridge, faced the brunt of the 12th SS Panzer Division's assault. The German tactical plan assumed that the Americans could be driven off the ridge within the first day, clearing the northern flank for the armored exploitation that was the offensive's main effort. The plan had worked against similarly positioned American units in earlier operations. The terrain favored the attacker. The German armor was intact and rested. The SS divisions were among the finest remaining formations in the German order of battle. Veterans, well-equipped, motivated by the specific ideological intensity that distinguished Waffen-SS units from Wehrmacht equivalents. The 12th SS Panzer Division had last fought in Normandy, where it had conducted the defense of the Caen sector with a ferocity that had made it one of the most feared German formations in the entire campaign. Its commander understood armored tactics at the operational level. Its infantry regiments understood how to assault prepared American positions. The plan for Elsenborn Ridge was not improvised or careless. It was professionally executed from the opening minutes. What it had not accounted for was the artillery preparation. The 400-meter killing zone in front of the American positions was swept by proximity-fused airburst fire from the first minutes of the German attack. Consider what this meant in practical, tactical terms. Infantry advancing in the open would normally take cover when artillery fire began, going flat, using terrain features, moving into any depression that reduced their exposure to incoming fragments. Against conventional artillery, this was sound technique. A shell detonating on impact with the ground sent most of its fragments laterally and forward, away from the detonation point. A soldier lying flat in a shallow depression, or sheltering behind a fallen log or a gentle ridge in the ground, was substantially protected. Against a shell detonating 30 feet overhead, the fragment pattern was inverted. The lethal fragments were moving downward. The depression provided no protection. The fallen log provided no protection. The only protection against an airburst shell was a solid overhead cover of the kind that only deep bunkers or reinforced structures provided. Structures that attacking infantry cannot carry with them across open ground. The German infantry advancing toward Elsenborn Ridge on the morning of December 16th did not have overhead cover. They had their helmets and their winter coats and the standard Wehrmacht infantryman's skill at using terrain, which was considerable and was useless against a fragment pattern arriving from directly above. 3 attacks on the first day failed to dislodge the American positions. The failure was not a result of American infantry's superiority or tactical innovation. The 2nd and 99th Divisions were good units, but they were not qualitatively different from the German formations attacking them. The difference was the artillery. Every battery that had been loaded with green-banded ammunition was firing a weapon that had been optimized for exactly this situation. Infantry in the open, attacking across terrain where no overhead cover was available. The proximity fuses were finding their altitude, 30 feet above the German assault formations, and detonating there with the mechanical reliability of a device that had been assembled to tolerances measured in thousandths of an inch by workers in 110 factories whose names are not in the histories. 3 more attacks on the 2nd and 3rd days failed. The northern shoulder of the German offensive held. The armored exploitation that Hitler's operational plan required never had the open flank it needed. Elsenborn Ridge remained in American hands for the duration of the Ardennes campaign, fixing the northern boundary of the German penetration and limiting the bulge to the corridor through which Bastogne became the decisive engagement. Military historians who have studied the Ardennes offensive in detail have noted that the German failure at Elsenborn Ridge in the first 3 days was decisive for the entire campaign. That if the northern shoulder had been pushed back as planned, the German breakthrough might have reached the Meuse before American reserves could have been positioned to stop it. The proximity fuse did not win the Battle of the Bulge by itself. No single weapon ever decides a battle by itself. But in the specific engagement where the German offensive's operational logic required success and found only failure, proximity-fused artillery was the dominant instrument of American defensive firepower. Feldwebel Richter, writing in his field diary on December 17th, added a line to his earlier entry. "We face not just American soldiers, but American science. Their shells think. They calculate. They decide when to kill. We are fighting the future itself." He was not wrong. He was also not entirely right. The shells did not think in the sense that Richter meant. They did not have intentions, did not make decisions, did not understand what they were doing. They had a single functional capability, sensing how far they were from a surface that reflected radio waves, and triggering detonation when that distance fell below a set threshold. By the standards of what would later be called smart weapons, the proximity fuse was primitive. It had no guidance, no target discrimination, no programmability. But by the standards of every weapon that had existed before it, it had something that no weapon had ever had: situational awareness. It knew something about its immediate environment. It responded to that knowledge. Every previous artillery shell had been inert from the moment it left the barrel. A projectile traveling on a ballistic trajectory, exploding when a timer expired or when it struck a surface, indifferent to anything between the gun and the target. The proximity fuse changed this. The shell was no longer inert. It was, in the specific, limited sense that the word can apply to an artillery round, aware. This was the revolution that Richter was feeling from the receiving end and could not fully articulate. He had the vocabulary for weapons that hit things. He had no vocabulary for weapons that responded to things. The distinction was not semantic. It was the difference between a machine and an instrument, between a device that did what its design specified and a device that adjusted what it did based on information from its environment. The proximity fuse was the first production weapon in history that belonged to the second category. The full account can now be assembled. In October 1939, Britain faced an arithmetic problem. The kill ratio for anti-aircraft fire was so bad that the country could not survive a sustained German bombing campaign if the mathematics didn't improve. William Bootman proposed a solution that required making a radar system small enough to fit in an artillery shell. British industry lacked the capacity to develop it. In September 1940, Henry Tizard brought Bootman's concept to America in a black box on a ship. He gave it to Merle Tuvey, who had spent the previous weeks crying over London on his radio, and was now handed the specific problem he needed to solve. Tuvey assembled his team at Carnegie. James Van Allen solved the vacuum tube problem that had defeated every previous attempt. Shock-hardened tubes that could survive being fired from a gun. 87 companies, then 110 factories, then 80,000 workers assembled the result. Women whose names are not in the histories did the precision work that made the production quality possible. The Allies held the weapon back from European ground warfare for 2 years, using it in the Pacific and over England. The operational security decision, worth more as a surprise than as a continuous capability, had no monument and no popular history. It is present only in its outcome, the shock on Elsenborn Ridge in December 1944, when the weapon arrived as something Germany had never encountered rather than something Germany had been studying for 2 years. On January 5, 1943, USS Helena destroyed a Japanese bomber with 5 rounds of proximity-fused ammunition. The standard kill ratio dropped from 500 rounds to 155. In the summer and autumn of 1944, British anti-aircraft batteries destroyed 79% of incoming V-1 flying bombs with proximity-fused shells. In the first weeks of the V-1 campaign, before the fuses were available, they had destroyed fewer than 20%. On December 16, 1944, the proximity fuse arrived in the European ground war. At Elsenborn Ridge, it held the northern shoulder of the Ardennes offensive and denied the German attack the open flank it needed to reach the Meuse. The Battle of the Bulge failed. The German army retreated east. 5 months later, Germany surrendered. Merle Tuvey returned to basic research after the war. In 1946, his colleagues found him alone in his laboratory, weeping. He had spent 5 years working to develop the weapon faster, to close the gap between the London bombing he had heard on his radio and the shells that could stop it. He said, "All those boys who died while we were still developing the fuse. If we'd been faster, even by weeks, how many would have lived?" He spent his remaining career in radio astronomy and seismology, seeking the distance from weapons development that the war had made necessary. He died in 1982. His name is not known to most Americans. James Van Allen went on to discover the radiation belts that bear his name. When asked about his wartime work in later years, he said simply, "I helped save lives. Everything else I've done pales in comparison." The shock hardening techniques he developed for proximity-fused vacuum tubes were later applied to the instruments on early American satellites, protecting them from the vibration of launch the same way they had been protected from the violence of being fired from a gun. The thread from the cyclotron building on Broad Branch Road to the Explorer satellites ran through the same physics. Lloyd Berkner, Richard Roberts, Henry Porter. Their names appear only in technical histories. The women on the production lines built the tolerances that made everything else possible, and are present in the record only as aggregate production statistics. The final numbers, which are the only numbers that answer Richter's question about what he encountered at Elsenborn Ridge, an estimated 25,000 enemy aircraft destroyed or damaged by proximity-fused shells during the war. More than 5,000 V-1 flying bombs destroyed before reaching London. Artillery effectiveness against entrenched infantry increased, in the specific engagement conditions where airburst fire was possible, from a baseline kill probability of approximately 5% to approximately 70%. Allied lives saved across all theaters and applications is estimated in the hundreds of thousands. $1 billion, 1940s currency. 87 companies, 110 factories, 80,000 workers, 6 vacuum tubes per shell. 30,000 revolutions per minute, 20,000 times the force of gravity. One woman's hands soldering one connection to one tolerance in one factory in Cincinnati or Silver Spring or any of 100 other facilities, and that connection surviving everything the gun could do to it, and the shell finding its altitude and deciding by itself that the moment had come. The shell thought. And in thinking, it changed what it meant to be under fire, what it meant to defend a city, what it meant to hold a ridgeline in December snow against the last armored offensive of the Third Reich. The future Richter named in his diary had been built in a cyclotron building in Washington by a man who had been crying over London on his radio, assembled by women whose names are not in the histories, held secret for 2 years while it was used where Germany could not recover it, and then released at exactly the moment and place where it would be most decisive. That is the forensic record. That is what the green-banded shells were. That is what thought looks like when it is manufactured at scale.